Okay, hello, my name is Alex, and today we are going to be doing this problem here. We're going to be finding the minimum depth of a binary tree. So given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Note a leaf node is a node with no children. So given the binary tree, so when it means null, it means that there's no children. It does this so it can basically define that 15 is a root of 20. Oh, sorry, a leaf of 20. And same for 7. So it does this in this sort of pattern. So it goes like that, sort of like Pascal's triangle. So anyway, so that's why they have to put a null to specify that there isn't anything there. Anyway, our challenge is to find the minimum depth. So in this case here, the minimum depth is 2, just from 3, which is 1, and then 2, 9. So whenever we get a question about binary trees, there's only really two ways that we can traverse a tree. Well, in general, yeah. So we have a tree and some leaves. Just give it a bit of variety. We can do breadth first search, which uses a queue. The traversal of a breadth first search would be something like this. So red here, then here, and here, 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 then here. So 1, 2, 3, 4, 5, 6, and so on. Or we can use depth first search. This uses a stack. So if we want it to know what it would look like, it would be 1, 2, oh boy, let me pick a different color. It would be 1, then 2, then 3, then 4, then 5, then 6, 7, and 8. It would traverse depth-wise, whereas breadth will traverse based on the breadth. Hopefully that makes sense. Anyway, so we have to pick which algorithm that we're going to use. Now in this case, we want to find the shortest path. So it would actually make more sense to use this. This should technically be faster for this problem, and I'll explain why. Let's just add another node here, just to make it prevalent. And okay, let's just use this example here. If we use breadth, we would check this one, see it has children, check its children, so 2, 3, and then we'll check 3, or this one here, and we would see it would have no children. And since this one and this one have children, and we really don't care whether these two have children, we can just return the value of our current counter from here to the root. So we don't have to check all of this. So we're essentially saving time, right? Depth first search would involve checking this, and then checking this, and then checking this, storing all these values in a, say, an array, and then returning the minimum value of that array. Which, we checked the entire tree, when in reality we don't really have to. Now say we removed all of this. So now the min depth, as you can see, is 2. So if we applied the breadth first search, check this one, see it has children, check this, see it has children, check this, has no children. We can turn the value, we can return the distance from here to here. And that's it, that's our solution. We avoided checking this. Okay, cool. So yeah, we're going to be going with this one. And later I may show depth first search. Alright. Boy, time for my super loud keyboard to get some action. Alright. Alright, so like I said, we'll be using a queue. I'll try and move my keyboard as far away from my mic. Keyboard is pretty loud. Anyway, stack.append root, and we'll just say, actually we don't want to append, we'll say we want to also append the value, so I'm going to make it a tuple. While q does not equal to, or while q is not empty, we're going to get the node and the current count is equal to q.pop, and we're going to pop the first element. Now if node.left does not equal to none, then we want to do q.append node.left and then current +1 because we're traversing down one. If node.right does not equal to none, q, it's the same deal. +1. Okay. Now, if they are both none, then that means that we're in a child node. And node.right is equal to none. We can just straight away return current. Yeah, that makes sense. I don't think we have to do a +1. Okay. We're going to test this out, we're going to run some edge cases, and we're going to see how it goes. Okay, so if, say, root is equal to none, turn 0, this should succeed if both root.left and root.right is none, because it would just go straight into here and return current. Let's try that. Indentation. Ah, boy. There we go, found it. Alright, let's give it a shot. Can I not write if statements? Oh my gosh, what has the world gotten into? Alright, delete this. Delete this. There we go. If root is equal to none, return 0. Fuck me. Oh my gosh, alright, let's just get rid of it. I'm triggered. I'm so triggered. Where is it? Fuck me. Where is it? These indentation... Unexpected indentation... Because I have to tab everything across here. Let's add that test case back. I can write if statements. If root is equal to none, return 0. Last place. Finally, some edge cases that I can think of. That one. Alright, let's submit it. You can see here I ran it plenty of times. Sometimes it runs for 64 milliseconds. Other times it runs for 48. Alright, so I'll tell you now, these two tests were depth first search, and I'll quickly show you how I did depth. I just don't know why it's so inconsistent. Yeah, and see now it's 48. So ideally this algorithm should be faster than depth first search. Let's just quickly implement that. So that's that. And now remember I said that we needed a dictionary, because depth first search is going to just return the first depth. So a good example would be 2, 2, 2, null, null. So I remove this. This is technically a stack now. And this should return 3. This will fail something. Let's just find out what fails. Yeah, this one. So if we were to draw this one out, what it actually looks like. Okay, remember it's 3, 20, 19, 20, null, null. So it's it looks like this. 3, 9, 20, and then 15, 7. Null, null. This is here. This returned that. We returned one of these branches here. Because we saw that both these were null, thus we just broke out the loop and just returned the incorrect value. So to fix this, like I said, we'll need some sort of array to hold up all our values. So dict.append that, and then we're just going to return the minimum of dict. Run it again, and we got 2, resubmit. There we go, 68 milliseconds. So the best time that this algorithm ran was 56, and the best time that the other one ran was 48 milliseconds. Yes, there is a difference that we can see. I'm not too concerned with memory. Technically, I think this one should take up more memory as well. Anyway, that's technically it. That's the problem, and that's also the solution. Anyway, thanks for watching. It's getting late. I have to wake up early tomorrow for uni and work. Oh yeah, that's partly why I haven't been uploading a lot, because of work. I work in the cloud industry. Maybe I'll make another video about it. Okay, thank you. Bye.